Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mountz. And our background here looks a little bit different than normal. We've taken the webinar on the road, and it looks like we have some other peripherals happening here. There we go. We have the webinar here on the road. We are here at our Alabama campus where we have our warehouse, a distribution facility, as well as our calibration and service center here in Foley, Alabama. And so it's really nice to be in a different location to help provide you with a little bit information about our topic for today, and that is how we can improve production efficiencies by implementing the screw counting process. And so as we look at a lot of torque failures and quality issues, a lot of those deal around a lot of the human error and aspect to the actual process that happens. And often we begin these sessions when we talk about the different types of risks that are associated with the quality and the manufacturing process. And we always mention over-tightening or over-torquing fasteners, as well as under-torquing fasteners. We also deal with cross-threading, these types of errors that help to really eliminate or help to actually not allow us to get the correct clamping force that we need for our components. But if we have missing components or missing fasteners within the assembly, then we no longer have any protection for the clamp load that we're trying to achieve. And so we don't have an opportunity to create any over torque or under torque or cross threading or those types of issues if a fastener does not get torqued at all. And so with that process, we do have the ability with the different power tools that are provided to be able to help eliminate some of these quality issues that may be affecting some in the production environment. And so how can we safeguard against these fastening failures? Well, first we can implement screw counting tools that do have error proofing capabilities that are built into it that allow us to be able to double check the process and help to control that human element. So it gives us the ability to track each fastener that we are using and to detect any fastening error that may happen. And so with the different types of processes with the counting and error proofing process, this really helps to eliminate the influence from the operator within the assembly process. And so this also can be integrated into a line management program. So if you are dealing with a PLC or you are dealing with other line control components, these types of screw counting and error proofing processes do allow for that type of communication as well. And so what are some of the detectable fastening errors that we can catch with a screw counting type of implementation? So first is going to be the different lengths of fasteners. So if you have the same thread pitch, the same size of a fastener, but they're just different lengths, we can ensure that the correct fastener is used for that particular application based off of the length of the fastener that's being used. So if we do use one that is too short or too long, we'll be able to detect that type of error. Along that same lines is going to be the thread pitch. So if the thread pitch is different, we would be able to detect that as well, along with the fasteners that don't fully get seated. So an operator may not necessarily be paying attention and let go of the trigger of the tool, and that fastener then is a lifted fastener or not completely torqued. We would be able to determine that. If there's missing components, so a washer stack that may be included or a gasket that needs to be in the assembly, we would be able to detect if that is there or not there. We can also help to prevent against cross-threading or detect when there is a cross-threading of an event that happens. And that can be really helpful if you are dealing with very short types of fasteners, where the cross-thread issue may be very similar to a seating type of torque, but we can still detect that type of fastening. And then if there's a cam out, again, this would be almost like a lifted type of fastener where the bit just lifts out and the operator lets go of the trigger. And then we can also detect if there is a stripped fastener as well. And then finally, if we're dealing in a situation where the operator necessarily can't see the fastener itself, so it is recessed and they're a little bit unsure of if that was done correctly or not, we can help detect all of those different types of errors in the event that the operator can't necessarily see what is going on with the fastener itself. And so that's going to lead us to our poll question for today. The question is, what common fastening failures currently are you experiencing? And we'll go ahead and launch that poll. And we have missing screws, cross-threading, stripping screw holes, screws not being seated, or screw cam out. So let's go ahead and launch that, and we'll give you a minute or so to answer those questions. And in that time, I'll get a drink of water. All right, thank you very much for participating in the poll. It looks like the majority have answered in the screws not being fully seated, followed by cross-threading and missing screws. So thank you very much for participating in that poll. And hopefully the information that we'll be giving you through the rest of the presentation can help address some of those issues that you might be seeing. And so when we look at some of the features of the screw counting system, obviously we touched on the ability to be able to track all of the detectable errors that happen during the fastening process. But we can create actually counting programs around the assembly process. So with one of the options, you have the ability to track obviously the number of fasteners that are being done. If you have different screw profiles, you have that ability. So say they may be the same torque value that you're dealing with, but they are different sizes of fastener. Maybe they have a longer length to them, or shorter, or that type of thing, but they would use the same torque. We can account for that type of counting. So a lot of the features that come with that, we kind of touched on with the line management and a number of those different types of features within the screw counting process. But the really big benefit is the ability to help error-proof the assembly and give the assembler the ability to make sure that they're doing their application or their operation correctly. And so when we look at some of the different options that are available for screw counting, one would be a system like this, which is our Scout 2 screw counter. It works in conjunction with a normal transformer style electric tool. And the way that this system works is it actually will measure the fastening process that happens for a particular fastener in milliseconds, and then we can create what would be an acceptable window for a minimum and a maximum amount of time for the fastener to be run down. If the fastener or the tool, excuse me, does reach torque within those limits, then that will be considered a good fastening, and it will go ahead and index to the count. If the fastener is torqued before the minimum time, that could be an example of a cross thread type of issue, then the system will reject that and give that a no good fastening. Or if we have possibly a stripped fastener, then that is going to be exceeding the maximum amount of time. And again, we would receive a no good for that particular fastener. And then if the tool is run for the correct amount of time, however, the tool itself does not reach torque, it will still count that as a no good fastening. And so those conditions must be met, must be within a time window and the tool reach torque for that to be considered a good rundown. With the with the Scout 2, you can have up to 8 different screw profiles that you can use, and you can also have up to 4 tools that can work in conjunction with the screw counter. Now, you can use this in kind of a cell type of build where you would be using one driver at a time. It won't allow you to have different tools plugged in and operating at different times for this particular setup, but it will allow you to use one driver for one profile, use another driver for a different profile, use a third driver for a different profile or a repeated profile. So it does give you that ability to have multiple tools with one ability or one item to be able to help with counting. And so these fasteners can, or this system will allow you to have up to 99 fasteners for one assembly. And so that is the Scout 2. Again, works with a standard electric clutch shutoff tool. The next option would be the use of a DC type of system. In this case, we're talking about our EC products. This type of scenario, we can actually create the assembly around the actual application where we can call out for a specific preset. So if you have multiple presets that you might be dealing with and multiple fasteners, we can build presets around those particular fastening items. So we have our torque, you have the screw profile. All of that can be encompassed in an assembly program that will allow you to be able to do that in a certain order, and then the controller will automatically change the preset based off of the assembly process. And so you'll see that in our example as we look at our demo process for the DC tool. But this one will keep count for each specific fastener set within a specific preset that is being used. And so that count will also be part of the process. And the error proofing aspect of this is instead of using a time-based system where we create the window of a minimum and a maximum time, the DC tool allows us to actually create an angle window. So we can have a minimum amount of turn or a maximum amount of turn for a specific fastener that we might be using for a specific assembly process. So that is the difference between that and the Scout, how it determines which actual error proofing type of controls happen between those two. And so finally, the third option would be the use of our DPC Touch, which actually is a location-based type of system where we only have power to the tool if the driver is in the right location for that. This type of system can be used with our electric clutch tools as well as our DC system. With the DC system, it allows the location to be controlled, the preset, that is being used. So we do have that capability where every fastener that gets torqued is done. It's done correctly, and the system won't index to the next location until we get a good rundown signal back from the tool. So that system, again, works in conjunction with either the electric clutch shutoff tool or the DC tool. In the demonstration part, we are working with the DC tool, and we're doing a small program. But again, it's a location-based type of error-proofing system, and it does allow us to be able to give visual instructions and guidance to the operator on where they need to be for a specific assembly. So we actually guide the operator through the whole process, and there isn't the opportunity for them to make a mistake in using the tool in the wrong location. So with that, let's go ahead and jump into the demo portion of our presentation. And first we'll go ahead and we'll look at our Scout product. And so here's our Scout. I've got a small thread block here, and then we have our electric tool. In this case, this is one of our BF brushless drivers, and it is connected to the transformer. And then the transformer is also connected to the port for the different tools that can be used. And so here you see A, B, C, and D. These are for the different tools that you can use. For our scenario here, I'm just using one tool for that. And then we have our ability to go ahead and set up a specific profile for a fastener. And so I have our thread block here. All of these fasteners are pulled up to a certain amount of angle, and we'll use those to go ahead and do our testing with this. The system does allow us to do what would be our measuring mode, and it will go ahead and calculate based off of the number of rundowns that we do. That will go ahead and allow us to basically automatically program the unit for a specific fastener. So if we have any questions with that, all we just need to do is we actually log into the controller, which I've already done, and then we can go to the different mode here, and you can see we're in the measuring mode right now. And so we'll have our minimum time here that it takes, and then our maximum amount of time. So I'll go ahead and run 4 fasteners down, and we'll see the actual values that we get for the rundowns. So let's go ahead and do that. So we're right at 322 milliseconds. And that was at 302, 341, and 341. So that is kind of how we can go ahead and we can set this. If we like those measurements, then we can go ahead and use this, and we want to go ahead and set this to be used with program 1. So we can go ahead and do that. We can go ahead and save this. Oh, did I just not save it? Then we can go back to our work, and let's go ahead and program the number of fasteners that we are using. And so to do that, I can go into our parameter section, and the first parameter is the count for number 1. So let's go ahead and set that to 4. Save that, and now we can come back into our operation mode, and we can now go ahead and run 4 fasteners down, and we can see if those are going to be accepted or not. So all right, so that one was within the limits, and it went ahead and accepted it, and we're counted down, and now we have 3 fasteners left to do. If we had a cross-thread type of an event where it would torque out right at the very beginning of the rundown, you can see we got our no good, and it did not count that. And so we can go ahead and run it down. Again, now we have 2 left. Good, okay. Let's say we went too long. Now we've got, again, our no good, so that would kind of simulate the actual stripping part of our rundown. And then finally, if we do the last one, now we've done that correctly, it will go ahead and reset and allow us to then move on to the next component. Now this particular system can be controlled and used with the I/O information that we have available. So if you have a particular input device that you need to control which program you would like to use, 1 through 8, that will allow us to use those types of input signals that can be used to call out a specific profile that needs to be used, or it can be done through the PLC selection as well. So we do have that capability to add some automation to this type of tool. But again, this is designed to be used in kind of a simple counting function with a standard clutch tool. So that is the Scout 2. If we look at our DC system, what you'll see here is currently right now I am in our model mode, and this is the mode that we use when we are doing an assembly process. And so again, if we wanted to do 4 fasteners, right now you can see we have a count function set for 2. We're doing 2 fasteners at 1 preset and then 2 fasteners at an additional preset. And so each of those will be counted for that particular part of the step within the model or the actual assembly process. So let me show you what that looks like when we do our programming. So I'll go ahead and log into our controller, and we can go to our model setup. And so we can have 15 different models or 15 different assemblies that are comprised of the 15 different presets that we have available to be used here. And so with our models, we can have up to 20 different steps within that model. And this one, again, is just very basic for us. We're using preset 1 for a count of 2. Then the system will automatically change to preset 3, and then we'll use that for a count of 2 as well. And so that is how the system can be used to create the assembly process. So if we head back out to our main operation screen, we can go ahead and do that. So now what we're looking for is we have our torque values here. We have what our RPM speed is going to be, and then we also have our count function. And so as we run a fastener down, we get our torque has been achieved, our angle has been achieved as well, and now our count function is down to 2 or 1 of 2. And so then we can go ahead and do our next location. And now we've moved up here. You can see we have gone to preset number 3 within our second step within this model. And our count function is now back to 2. So we can go ahead and run this. And if we had that similar type of cross-thread type of error, we would get a notification from the tool, and again, it would not count that. If we had a stripped type of fastener, once we achieved our maximum amount of angle, we would get an error, and again, it won't count that as a good rundown unless we go ahead and get those particular settings accounted for. And so now we've done the different locations here, and then next would be the use of our DPC touch. For this, I need to move out of our model mode and we can move into our preset mode. So this is how this works. So I'm just going to go ahead and change the actual mode that we're using it. And we can come back out. And now for this case, I'm using a different set of fasteners here. So I'm going to pull these two back up to a certain degree here. So let's go ahead and change this to preset 2. This should allow us to do that correctly. So in that case, I was just using a feature that allows us to actually run the tool after it's been torqued up to a certain amount of turn. In this case, it's 3,100 degrees of angle up, so that they're basically back to where we started. And now, since we're in our preset mode, and you can see we're on preset 2 here, when I go ahead and I add the DPC touch to this, go ahead and add this, and go ahead and power this on. And now it's brought up our program where we want to go ahead and do our fastening. But in this case, it is showing us that our tool is locked right now. So there's no power to the tool whatsoever until we get to the correct location. Once we get to the right location, you can see that we do have a green light in our status. If we move outside, it changes to red. And again, in this case, we are moving between preset 3 and preset 1 for every other fastening. In this case, we're using preset 3. If we go ahead and do our rundown, and we get a good torque up signal, it does allow us to go ahead and index to the next location, which is our second location here on this particular fastener. If I try to go to a different fastener, it does not allow us to do that because, again, we only have power to the tool when we're in the right location. You can see that it's now changed to preset 1, and so we can use that. We can go ahead and run this down. Once we got a good signal here, again, it will go ahead and allow us to move on. If we had that same type of cross thread issue, or again, if we were going in the right location, but the fastener had stripped, again, we would have our angle exceeded. And we can go ahead and run this down. And now we have our job complete signal. And then the system will go ahead and reset, or there's some other functionalities that we can do with this particular tool and the DPC touch. We can have up to 255 different programs. The system can handle 255 different steps within one particular job, so we can error-proof the entire assembly process. There's input and output management and a lot of other different things that we can do within the assembly process. But in this case, since we're dealing with just the screw counting and error proofing functionality, that is kind of what we're showing you with these different examples. So depending on which type of power tool you might be using, which level of error proofing you might need from an application that may be very critical, where you'd want to use maybe the DPC touch that would allow you to be able to control and lock down the entire assembly, and the operator can only do the application within the certain step, and unless that step is done, it does not allow them to do anything else. Or you have an application that may not be as critical, and you are using a clutch tool, you can do the same type of error proofing and screw counting with the Scout 2. So with that, I hope you gained some information about how you might be able to implement screw counting to help you with your processes. And with that, we'll go ahead and move to our question and answer. Today, Vinka will be compiling the questions. So Vinka, do we have any questions?
We do, Dave. So our first question is, how many screws can you count in a sequence?
So with the Scout, you can do up to 99 fasteners per the profile. If we work with the DC tool, again, we can do 99 per step. So if we have 20 steps within our profile, each step can have 99 of those. And then if we're working with the DPC Touch, then we can have up to 99 and with our 225 different steps that we can use as well. So that would be the different ranges of the different counts that we can do with the different styles of tool.
Great. So the next question is, for line control, can you stop a part from moving down the line if there's a fastening error detected?
So yeah, that's possible. Again, we can use the input and output communication to be able to send a signal to line management saying that, okay, we've completed that particular job or assembly, and we can go ahead and move the line. So there is that ability to have that communication. We can also use what's called a midpoint signal as well to help with the line control. So yeah, by use of the inputs and outputs, we can go ahead and send that to line control.
And our last question is, when setting up the screw rundown time, do you recommend doing 10 or 20 test samples first?
So typically, you want to do as many as you can in the same type of environment that the actual rundowns will take place. So that's going to give you a better sample size to be able to gather the basically self-learning portion of the rundown. For example, for the Scout, with the DC tool, we can actually see what that angle is. There's also an automatic learning mode for that as well. But typically we want to be able to do as many as we can to help us have a more accurate sample for those particular measurements. We can always go into the different parameter sections for each of those as well, so that it makes for a good starting point. You can also go in and fine tune the windows however you see fit. So if you need to open those windows up a little bit more, you can do that by extending the maximum time and shortening the min time, or same thing with the DC tool with the angle. You can tighten that angle up or open it up however you see fit. So,
thanks, Dave.
All right, if that's it for today, I appreciate your time, and hopefully we'll be able to be back here to Alabama, our Alabama facility soon, to do another on-site webinar. But until then, thank you very much, and we'll see you next month.